Wonderful. Thank you very much. Well, colleagues, great to be here. Happy New Year to everyone, and welcome to 2021. I'm going to ask people to mute their mics if possible. I can hear a few mics that are still on, so if you can mute those, that'd be fantastic. So welcome again. This is the first digital discovery session of the new year for the UN Environment Program. And these are really opportunities to conduct a peer-to-peer deep dive on a digital transformation topic. Now I'm going to ask if colleagues can mute themselves one more time because we've got a lot of feedback. There we go. So this is an opportunity to conduct a deep dive with colleagues in a safe space on a particular digital transformation topic of interest. And today we're going to be looking at the question of digital twins. And I know many colleagues have probably heard about digital twins in one capacity or another. I know there's a lot of talk about them with respect to, for example, airplanes and factories and even cities. But today is something special where we're going to be talking about a digital twin of the Earth. And this is obviously a massive vision and a massive undertaking that's being developed by the European Commission. So welcome to this session. We have three excellent panelists today. First up, we have Christian Kirchsteiger. I hope I got that right. Christian, could you just wave, put your camera on and wave for everybody, please?
Unfortunately, I cannot put it on because then I'm immediately crashing. So I'm waving acoustically.
Wonderful.
Good afternoon to everybody.
Thanks, Christian. And Christian's with the European Commission DG Connect, and he is responsible for strategy development of EU policies for smart infrastructures, including energy and transport, and is obviously directly working on this digital Earth, or the digital twin of the planet. Then we have, next up, we have Peter Bauer of the European Center for Medium Range Weather Forecasts, otherwise known as ECMWF, a nice acronym that slips off the tongue. Peter, could you just wave quickly? There we go. Thanks, Peter. So Peter is the Deputy Director of Research and Program Manager of the ECMWF Scalability Program. And then finally, we have Peter Messmer from Nvidia. He's the Senior Manager for HPC Visualization and Development Tech. And we also actually weren't expecting Alison to join us, but we also have Alison Lowndes from Nvidia on the panel as well. She will be co-moderating with me today, and we thank her for joining us today in this circumstances she's under. So the agenda for today, we're going to kick off with about five minutes from Christian, who is going to set out the European Union policy landscape with respect to the Green Deal and some of the big visions on digitalization. Then we're going to hand it over to Peter Bauer for about 30 minutes to present the Destination Earth program and the digital twin of the planet and what this means. And then we're going to do a final 30 minutes with Peter Messmer from Nvidia, who will go into more information about sort of the latest tech in terms of visualization of complicated variables and you know how different interfaces can be applied into this context. So we'll kick it off like that. I wanted to say that this is going to be sort of, we're trying to do three things here. We're trying to understand what the digital twin of the Earth will be. We're trying to understand what the use cases will be. And then importantly for UNEP, how can we leverage this, right? How can we incorporate this into our vision for our digital transformation program? And how can we begin to leverage it within the World Environment Situation Room? So I'm hoping we can touch on all three of those questions in this presentation. So before, or without further ado, let me hand it over then to Christian to open up with some remarks around the context setting for the European Green Deal. Now, Christian, you wanted me to present your slides, so let me just share my screen and open those up for you. Just give me a second.
That is perfect. Thanks, David.
Assuming you can see that?
Yes, yes.
Okay, yes. The floor is yours.
Well, thank you very much for inviting the Commission to talk about this I think, truly exciting initiative on Destination Earth. Well, as you see, I have only 2 slides apart from this little little headline thing. Essentially, I want to talk about 2 things. I would like to, before giving the floor to Peter Bauer, who will really talk about the, let's say, the meat and the technical substance of the initiative. But before doing that, I think it's necessary to talk a little bit, or to introduce rather, the policy landscape, the EU policy landscape of Destination Earth, or around Destination Earth, and how we come from this landscape to, and these, let's say, these underlying principles to the basic ideas and concepts of Destination Earth. So if we could maybe go to the second slide, please. The second one, please.
I'm on the second one. Are you seeing it?
No. Still with the...
You're still on the title screen?
Yes. Now we are. Yeah. Okay. No. Let me start with the very old concept of sustainability. So this triangle of environmental, societal, and economic effects, all interconnected and all underpinned nowadays by the digital dimension. So a classical dependency, of course, is between environment and economy. And as we all know, during the COVID pandemic, economic activity slowed, causing a reduction in carbon emissions, which is very good, but leaving the EU, and not just the EU, facing recession. So it's good for green, but bad for the economy and the income of people, with longer-term societal effects. So as a response to that, the Commission, the European Commission, came up in the second quarter of 2020 with an rather ambitious COVID recovery plan with a Green Deal at its core, which is called this Next Generation EU. This plan, this recovery plan of this pandemic, aims to create a greener, more inclusive, sustainable and digital Europe, and increase the resilience to future crises such as the climate crisis. So in that sense, this is an example of an integration of these 3 dimensions, all of which are then underpinned by digital. Now, concerning the climate crisis, already in November 2019, so before COVID, the European Parliament, as you might have read or heard, declared a climate emergency, asking the Commission to adapt all its proposals in line with the famous 1.5 degree Celsius target and ensure that greenhouse gas emissions are significantly reduced. And in response to that, the Commission then unveiled in December 2019, so just before the COVID crisis, the European Green Deal, which is essentially a roadmap for Europe to become, by 2050, a climate neutral continent. So the first steps under the Green Deal include, and all of them have been presented in the first 2 quarters of 2020. So already when the COVID pandemic was evolving, the list as shown here in this list of bullets aimed at an integrated view of all these 3 sustainability elements, including also the social dimension, but realizing actually all these highly ambitious targets and goals of the Green Deal means being able to check the relevancies of these challenges, to monitor them, and finding cost-effective mitigation strategies. So in a sense, this requires a kind of compass for policies along the 3 interrelated dimensions of sustainability: green, economic, and social, and digital being the actual enabler for that. Now, I'm mentioning that, and I'm explicitly referring always to COVID in order to show that essentially the Green Deal ambitions are independent of the, let's say, of the economic consequences and the economic impact of these other crises. So to come back to this interrelationship of sustainability goals, the key role of digital is explicitly recognized in the Green Deal, confirming that essentially digital technologies are a critical enabler for attaining the sustainability goals of the Green Deal. And furthermore, this goes really a bit in more detail and specifying explicitly that to be able to predict and manage in the future environmental and not just environmental disasters, to do this, the Commission will bring together the scientific and technological excellence available today to develop what is called a very high precision digital model of the Earth. Now, this is somewhat the founding document for this destination Earth. And if you again have a look at this bullet list of the Green Deal, this is in a sense at the same time its work program. So meaning to provide dependable foresight on the extent of challenges in relation to these issues and the mitigative options. So with regard to environmental disasters, climate change adaptation, sustainable agriculture, and in relation to that, food security, pollution reduction, clean energy, and biodiversity. And as you will then see in the next presentation from Peter Bauer, this corresponds pretty much to the thematic digital twin models which are to be developed under Destination Earth. Now to the next slide, please. Yes, for the actual design of this, how can I say, this so-called compass for the Green Deal, in order to be successful, meaning to have an impact, we take as usual, I would say, the lessons from real disasters, which is the problem of foresight. So it proceeds only if it is triggered by a disaster. So let's take again the example of COVID. So when one day countries around the world will emerge from our current lockdowns, I think it will become quite apparent that effective solutions to key societal challenges can be developed and then proposed to decision makers if they integrate best available knowledge. And this leads to the concept of the digital twins, about which Peter Bauer will then talk. If these proposed solutions are delivered in real time to the relevant people from across the spectrum of stakeholders, so policy, science, and business, and if they also explicitly show the different degrees of the underlying quality, meaning the maturity of the information in order to be useful for decision support. So this was somewhat the basic thinking, and still is, underlying Destination Earth. And practically speaking, this then means provision of an open user-centric knowledge generation toolset with very high precision of scenario predictions in a format which is usable or actionable for non-experts, essentially also. I mean, for example, from the policy domain, and which includes this before mentioned explicit indication on the trustworthiness of results. Not to succeed in delivering such an truly ambitious service, convergence of many different scientific disciplines is necessary, together with convergence of digital resources of a European level or of a member state level, which are then the enablers of these scientific ambitions. So in that sense, Destination Earth is about convergence of existing resources and new modeling and data developments. But last not least, Destination Earth is very much also about an open environment, an open collaborative environment, and an open development environment. And therefore also about a linking of knowledge, models, data, and policies from a And yeah, I think it is in this context that we very much look forward also to building cooperations with international institutions and partners, such as the United Nations Environment Programme on Destination Earth, for example, via common use cases, digital twins, and so on. And yeah, I hope we can put that in the center of our future discussions. But all this was just a little policy blah blah introduction. The real meat of the project will now be presented in the next presentation by Peter Bauer from ECMWF.
Thanks very much, Christian. Before Peter kicks off, I just wanted to ask two quick questions. Can you just remind colleagues what is the financial landscape associated with the Green Deal? What's the financial envelope associated with the Green Deal, and then what's the financial investment in Destination Earth?
Well, we're truly talking about very huge amounts. I mean, take for example this recovery plan, now this next generation EU, which is in the range of 750 billion euro. With all kind of new financing mechanisms and direct taxation for the first time and so on. Well, the envelope for Destination Earth without having a budget so far, because the entire European Union does not yet have a budget, as you might know. But we are certainly talking about substantial amount of money, so in the order of 100 million euro or more. And one has to say, actually, the budget is coming from essentially, or at least from two different lines. One from the Digital Europe, so-called Digital Europe program, which is the, let's say, the more technological budget line, and the other one from Horizon Europe, which is the future research program of the Union.
Great, thank you very much. Now, colleagues, this is meant to be an interactive session, so please, if you have a question for either of these presentations that are coming up by Peter and Peter, just put your hand up in the digital list there, and I will try to find a moment to sort of interrupt Peter and ask the question. So do feel free if there's ever a moment of clarification or some kind of additional question, do put your hand up and I'll try to call on you. So without further ado, Peter Bauer, the floor is yours. And Peter, I think you might be on mute.
I might be. So, but you can see my screen, no?
I can see your screen and we can hear you now.
Oh, perfect, thanks. Okay, a bit more background to the actual meet as Christian was describing it about the digital twins. And I think actually Christian and I now go back about a year, I think, since we started to define this program with a bit more detail. There is, of course, a history to this. Destination Earth didn't just come up within the last 2 years or so. There's been initiatives and ideas around such a concept for some time from different communities. And the one I participated in, at least, was called Extreme Earth, and it was submitted about 3 years ago, also to the European Commission as a flagship proposal. A flagship proposal, just like the Human Brain Project, for example, which was I think the first flagship proposal that's still running. And at that time, we didn't make it. We didn't survive the competition with other projects. And then the flagship program was stopped altogether by the Commission. And then we tried to turn this into something else and converge with other ideas. And this is where Destination Earth, I guess, eventually came from. I want to describe a bit of background information because, you know, Earth system science has a long history. Prediction and observation capabilities have a long history. And programmatic backup in countries and international organizations all over the world. So kind of we have to place where Destination Earth sits here, why we need it, and how we want to add the features that it promises, and why it's timely to do that now. And I'm going to go back a bit to something probably most of you are actually familiar with, is the annual reports by the World Economic Forum on global risks, climate change and extremes. I'm sure most of you have seen those. So that's an annual assessment of the likelihood and impact of different types of risks, some of which are related to climate change, some aren't, but they put them in a certain type of ranking in terms of likelihood. So that's the possibility that these actually occur, and if they occur, how impactful they will be in terms of loss of lives and cost. And so, in the top right corner, you would say those are the ones that are really, really hard hitting, because they may not be very likely, or some of them are actually likely, but they're certainly impactful. So the top right corner is the worst spot to be. And there you see already the topics that we're focusing on, and that explains why we're focusing on them in the first place. There's climate action failure, which relates to the carbon neutrality that Christian has mentioned. There's extreme weather, there's the loss of biodiversity and natural disasters. And if you have a system that provides much better information on those, that will also be a system that enables to deal with the consequences in a much more effective way in terms of adaptation, mitigation, prevention. And this is where we're hitting. Just last week, I came across this publication. This is from the National Oceanic and Atmospheric Administration in the US, so the US Weather Service. And they published on their website there a summary of the billion-dollar disasters over the last 40 years. And these are billion-dollar disasters only in the US, so you could do similar statistics worldwide, which is what United Nations organizations do or the World Economic Forum does. And if you look at these numbers, they're really staggering, So over the last 40 years, 285 disasters passing the $1 billion impact threshold, and with a total cost of nearly $2 trillion, So if we're talking about programs like Destination Earth that may cost, I don't know, hundreds of millions, compared to these numbers, this is really no money, and a very good investment. But statistics of these are well available and widely available in the community now, which is very good, which will also allow us eventually to characterize and quantify the positive impact that projects like Destination Earth can actually have on such statistics. So the disasters will occur in any case, but the mitigation and adaptation should reduce cost and should save lives. One thing that is rather new, at least where I'm coming from, I'm an atmospheric physicist. I work in an organization that does operational weather prediction globally. We are linked to users, and we do feed our data into all kinds of impact sectors. But to integrate these impact sectors and to think more rigorously along value chains or impact chains is also new to us. Because if you think of a Destination Earth framework that really feeds end users and that does, fulfill what mitigation and adaptation to extremes, for example, requires, it means that you not only put data somewhere that we produce with the global forecast model, but that you think much further into where this data lands, that you equip the communities, which are in most cases actually non-scientists, non-experts, with the tools, with the knowledge, with uncertainty estimates and actual exploitation tools, so that they can interactively work with what you produce in the first place. So this value chain example has been published by a colleague of mine in Germany some time ago, and it's a weather extreme. So weather extreme on the, let's say, weekly, monthly time scale, which relates to a certain weather pattern in the atmosphere that's fairly stable and tends to sit over an area for some time, a couple of weeks, let's say. And in this case, causes the co-occurrence of heat waves and droughts. So temperatures above normal, precipitation below normal, okay? And we had good examples of that in 2007, in 15, and many other years. And if you look at, the just recently published Copernicus statistics on the above average temperature statistics of recent years. The past decade has been extremely bad, and certainly supporting systems like this or features like this. And then, if you have something like this, which is what we do, we produce these maps here, but then we stop basically at that interface here, but you have to think that through, because heat wave and droughts create vegetation stress, which has an immediate impact on crops, but can also be supporting forest fires and stronger fires and longer lasting fires, causing air pollution. So not just destroying stuff and killing people actually, but also causing air pollution, which has effects on mortality, but also through the crop failure branch here, effects on economy and potentially social instability. So it's really, really valuable to think across these lines. And ideally, you have the system that rigorously applies scientific methods to model the entire value chain across all these potential branches at all scales. So how good are we at that? And when I talk to people about climate change, for example, many people think, and many politicians actually think, okay, the science part is done. We know we have a Paris Agreement. We know the famous 2-degree threshold that we try to stay below. So climate science is done. So that's by no means the case. So by no means we have the level of reliability and accuracy in our predictions or even monitoring to be able to say how weather regimes and therefore extremes will develop in the next decades or the next century. And this publication is an example of that, where one took the same climate forcing, so the same long-term change in atmospheric composition, so CO2 changed, methane changed, so all the greenhouse gases changed. And then you apply that to different types of models, or different models, in this case, 4 different models. And while these models more or less agree in terms of how they translate that forcing of CO2 into average temperature changes at the surface, this is why we are so certain about global warming, and maybe to a certain degree about what that means in terms of precipitation, in terms of dynamics of the atmosphere. So how does that actually change wind or weather patterns is really, really uncertain. And these 4 figures are really, really different because they show the near surface wind speed response to such a forcing. So these 4 models might agree in temperature, but they widely disagree in wind. So they will disagree in a prediction or projection of what global warming means in terms of extremes. So there's a lot more to do. The other part is that link again between climate science or Earth system science and these value chains I mentioned, or in particular what it means in socioeconomic terms. And there was just a recent publication here, that was end of last year, I believe, that makes a very strong point about that. That basically both sectors that right now we are at the front end of the production of Earth system data, and at the receiving end of trying to translate that into impact sector relevant information and make decisions of policies based on that, they should look more closely at one another. So climate science must be more driven by what questions in the socioeconomic framework are actually important, while the impact sectors must look more strongly upstream and tell us what they actually need and apply more scientifically rigorous models and quantification methods as we do actually on their impact sectors. So we need to come closer to one another. That's what that means. So, there's a lot more to say about this, for which I don't have the time. But in the end, it all breaks down and comes down to necessary breakthroughs. And we formulated 3 leading up to Destination Earth. And if you want to have a look at these publications down here, they were triggered by at the time when Destination Earth went public. So it was autumn last year. So there's a nice science article here. There's something in the New Scientist as well, and another one more related to the digital impact of that related to supercomputing in HPC wire. But all of them are written at a level that everybody can understand. So the main 3 points that we're making are, on the one hand, you need much better models, and I showed you what I meant with that before. You need to have a better capability of combining them with observations, which also enhances our requirements to produce observations and make that data available in the first place. So one thing is really on the science front end. And unfortunately, that has a very big computing footprint. And Peter Messmer will focus on visualizations, I guess, later, but he certainly has an opinion on HPC footprints and data handling that comes in the wake of Destination Earth. The second one is this integration and these two communities coming closer together. And Christian mentioned the important point. It needs actionable information, not just information in terms of rain rates and wind speeds or extremes or gusts or whatever, or global warming, but it needs actionable information. So, and that is actually impact sector dependent. So for somebody working in the energy sector or in agriculture, water resource management or finance, what actionable information means is really, really different. And also what quality means. What is useful, potentially useful information for one in the energy sector may be entirely useless for somebody else. So we need to make sure that the quality information is available to begin with, but we also need to understand at what stage information is actually useful for somebody in finance and below which threshold it's used less. And that's different again for energy, and so we have to understand that for everybody. That's an important part. And the last is really, really digital infrastructure based, and that's what Christian mentioned as the open and interactive access. So our communities have been separate so far. We have very good and very effective value chains already existing. We have service infrastructures everywhere. But what's really missing is this open and interactive access. Nobody in energy, food, water, or finance can do much about the data that's coming from upstream that we produce, for example, in weather and climate. These workflows are not accessible to them. And as I said earlier, in most cases, they don't have the tools to deal with the data, to interpret the data. There's an incredible translation threshold, and we need to change that. We need to have non-expert access and intervention, and I'm going to come back to that at the very end. So these are the three big points of Destination Earth. Twins, I heard that many of you are involved in several projects, so digital twins per se probably don't need much introduction. But this is a nice slide I put together here, case in our context. This one here on wind farm engineering is particularly interesting. That's just a small example, of course. In terms of the Earth system, a digital twin, that's a larger enterprise, but it's certainly relevant in industry for creating a product, for running production, and then for monitoring and enhancing performance. And I think in our case, all of these three elements apply equally, probably in different forms than compared to a production process in a factory or a space shuttle or something. But the logic and the philosophy of the digital twins apply equally. So for us, that means that we also have a continuous simulation and observation framework. So at the core, at the heart of the twins is a simulation framework that we try to constrain with observations. Even today, us at ECMWF, we're using off the order of 100 million observations per day. That's going to grow in the future in terms of volume diversity. So we know how to do that. That's why we want to use our methods of combining simulations and observations for Destination Earth. The other is performance monitoring. So this is about quality and resilience and stability of your system, which digital twins require, which we do in our system as well. I mentioned user interaction. Right now, we don't do that. So we really need to open up our workflows to be able to do that. And then apart from operational production, in the end, you also want one of your users is of course, energy, food and water, but another is actually the research community. So I said we need to open our infrastructures to non-experts, but you also want to make more and faster progress for research. So you need to enable these systems also for scientific theory and adaptation scenario testing, for example. So I can talk more about the what's inside the what's in the tin. So what's really at the core of the digital twin, but maybe I can do this in response to questions. So as I said earlier, we will use very sophisticated simulation models and the whole lot of observations that we have available. This will grow, the capabilities will grow, and I mentioned both have big digital footprints in terms of computing and data handling. So the present idea is to have two different types of production modes in destination Earth. One being more continuous. So there would be a backbone system that integrates simulations with observations that produces products. These products ideally go all the way through these value chains that I mentioned. But one important aspect of openness is on-demand options where users, even expert users or non-expert users, can actually drive the system themselves. So we educate drivers and we allow them to drive the car to a certain degree. And this will evolve as destination Earth goes. Some of that can be triggered by users. So if there's a specific user demand for doing something. If you think extremes, you could also say, okay, I have my continuous system. If I see that a prediction shows an extreme event occurring over Southern Europe, let's say, I can also say, okay, that is important enough to trigger on-demand specific, more tailored to that extreme event subsuites as well, that produces more data, better data, fresher data, use more observations to upgrade the level of information that we have available for that particular case. So there's a more static system and a more flexible system in that production. So coming back to the latter, this on-demand system would, for example, if you take a map like this and a prediction system would tell you, if you're looking at extremes, there's something going to happen in a week here and in 2 days there. You could then have several on-demand opportunities for upgrading in those areas your system by resolution, by refresh dates, by adding machine learning models that look at specific aspects of that translate a weather information into flood risks or landslide risks, air quality information and health and fires, for example, or other things. So that's kind of the idea of how we have these two production modes and how they are subset. And of course, that needs a different type of workflow management. This is something many of you may not care about, but for us, for example, running an operational system at ECMWF for weather, we know very well how much effort such an on-demand system is, because it also means that you have a very resilient workflow management and that you have access to infrastructures, means computers and data handling systems that can actually deal with the implications of that. Machine learning is an interesting one for everybody, certainly for us. Again, another publication from Markus Reichstein some time ago about the role and potential of machine learning in Earth system science. And I think the most important part in this paper is that it goes really both ways, where you draw from information systems and you derive knowledge from that. That's about, for example, translating weather climate information into something that's related to health and finance. But there's also a lot to learn from these impact areas, because they can drive that integration of their components into our Earth system model, so that helps us tailor our systems so that it provides better information or data in the first place. Altogether, we see the main points of potential for destination Earth regarding machine learning for acceleration in computing. So this is really to reduce the footprint. Same for data. Extraction of information, so that's this axis here. And then the translation between science and impact sectors. This is both axes here. There's a couple of challenges, though, and I think it's worth mentioning that because right now machine learning looks like it's a miracle and a magical source of information. I think it's important to be aware of the fact that machine learning doesn't create information. It can only be as good as the data it uses to be trained. And so there are certain issues that one has to keep in mind. The main three are summarized here. There's a consistency issue. If you just train machine learning or data-driven models with data, the machine learning methodology has no idea whether this is about something natural or synthetic. So it doesn't necessarily respect the laws of nature. That could be an issue. They're very good approximators, but you don't necessarily learn anything about the laws that creates the data. So we need to have cleverly designed machine learning methods to help us better. And in certain aspects, there's an interpretability issue. So, you might find strong correlations between data, but it may mean nothing about why this correlation exists, and it may just be a coincidence. So causation and correlation is not the same thing, and machine learning cannot help you with that. Just wanted to say that. I mentioned footprints before. We did a rough estimate of what the footprints actually would be. So you say, okay, I have my two production modes, continuous and on demand. I assume a certain system size, spatial resolution, refresh cycle, how many observations I want to take, blah, blah, blah. And then I make an estimation, given the systems we run in operations today, of how big that system would probably be. So how big a computer do we need to deal with that? And when we do that, such a calculation, we end up with probably machines that sit in the top 5 or top 10 of what's available today in terms of supercomputing. And these are expensive machines. These are 250 million plus machines, okay? And we're talking about data amounts of data that certainly people on the back end in the impact sectors can't handle. So it's really something where we as the ones producing the digital technologies enabling all this need to think very hard about the engine that we built and how we break this down and make this manageable, and in the end really benefit from these 3 breakthroughs I mentioned before, and not get lost in translation or computing. There is a lot of technology on offer. There's a new concept actually that goes way beyond HPC and big data, the 2 classic ones that we grew up with over the past decades. It's called now the digital transcontinuum. And what's up here in terms of cyber-physical system actually relates to digital twins. So there's lots of elements that contribute to that, which is called that transcontinuum. And ideally, we exploit the technologies around that in a perfect way, in a synergetic way, in support of Destination Earth. But some of these new technologies are really, really hard to deal with, actually. The fact that it's a better, faster racing car doesn't mean that we're able to drive it, okay? And there's been a New Scientist article about that already 2 years ago with that title, which tells you the story. So some of that is really not so easy. And it's not just buying a bigger machine for running a bigger problem exercise. There's a lot of digital engineering under the hood that we need to deal with in this program. So the digital twin concept is ideally versatile. So that's what sits at the heart of it in terms of models, observations, the way we bring the two together, and these software and hardware infrastructures. Ideally, is generic enough that it doesn't serve just one use case, but multiple use cases. So that's why we came up with this digital twin engine concept, which contains these components. But you could think of these components being applied in a quite wide context, actually. So that's your engine. These you apply to create digital twins. So these would be the digital replicas of A, B, or C, for example, weather or climate or storms or floods or pollution or food or water or something. And so you have the same engine, but that engine sits in different types of cars. One you do racing with, one you do shopping with. And then lastly, these digital twins serve multiple use cases. And that is then, do I use that car for traveling, or do I use that car for go to work or for go to shopping, going shopping? As you go from left to right, you diversify. And so the heavy development parts are fewer, and the application cases are more. That's the idea. And of course, the users are very important. I mentioned before, and Christian mentioned that as well. Ideally, this is increasingly co-developed and not left to, the Earth system and HPC people here, and everybody else has to take, what they understand or can handle. Ideally, this comes together and is driven by users all along, including the concept of uncertainty. And really, really important is this interface, which right now doesn't exist as effectively as it should be. And this will be a critical part in Destination Earth to break the barriers between, the expert side on this, the expert aspects on this side, and the actual application, and turning this into value aspects on the right-hand side. And I will stop with this. We have with the two colleagues, I wrote a commentary in Nature Climate Change that will be out beginning of February on particularly this user interaction aspect, where we really say, at the end of Destination Earth, what you would like to see is that there is somewhere a Destination Earth engine running. And then regardless of whether you have a weather application case or something about, forest or climate and something about crop, you don't need to be the expert that sits here. You don't need to understand what's going on here, but you have access to it. Not just in terms of data, but in terms of models that are derived from it, and you can actually influence how this is configured, that produces the data for you. It's like an iPad, you don't have to understand what's inside the iPad, but it's very easy to use as an interface, just as an analogy. And with this, I would like to stop. Thank you.
Wow, thank you very much, Peter. That was a fantastic opener into the whole Destination Earth vision and as you say, the full value chain of how it could potentially be used. Thank you very much. Before we go into the next presentation, I want to do a quick round of initial questions from colleagues that might want to clarify any points. I saw that Monica had been in the chat asking a question. I wanted to know if Monica wants to take the floor to open up a set of questions.
Yeah, thanks a lot, David. Really fascinating stuff, and I've always been interested in this for the last, I guess, 30 years of my career. So nice to see evolutions going in this direction. But having spent the last 18 years working on the policy side of things, we always talk about science informing policy, and you talked about the Paris Agreement and whatnot. But given that everything in an Earth system's perspective is connected, how do we look at well-meaning policies that are enacted in one area that may lead to impacts or effects on Earth systems from small to large that take your models in the wrong direction, or they have counterbalancing effects? Are you looking at building in policy impacts on environmental conditions or systems, so that you have that feedback of well-meaning policies or perhaps non-action where you have perhaps science deniers who say, oh, it's not that bad, we don't need to go that direction, the science is incomplete, we can't base our decisions on something with this much uncertainty, and you choose not to make a policy. Where is that feedback? Where is that loop? And particularly from the UN's perspective, since we deal so much with policy. Thanks.
No, you certainly would like to have that two-way interaction. So it's not just a system where you have a frozen environment or Earth system environment, and then that produces an estimate for what's going to happen in 30 or 50 years, and then you can develop a policy because you believe the data or you don't. What you really want is a level of interaction, and if there is an aspect regarding policies, for example, for curbing CO2 or for replanting rainforests or something, you would want to be able to test that within the system. I doubt that this is going to be available in the first stage, so at the let's say the first phase after 2 or 3 years of the program, but that level of interactivity is certainly what you want, because we want to enable a water resource or food resource management policy to test out scenarios of action or interaction in the system and see what it means to them. Of course, with an understanding of uncertainty, so and that's really important. We do this in weather already. We produce uncertainty estimates, and you want to propagate it. That's what I meant with, applying rigorous scientific methods also to the impact sectors. You want to understand actually whether the system gives you enough certainty on what you're trying there interactively, so that you're confident enough in what you're actually eventually going to do in your policy. But in stage 2 of the program, that level of interactivity is certainly part of the idea.
Thanks, Peter. I can see we have 2 hands up. I think Christian was first and then Alison was second. So Christian, please go ahead.
Right. Just to follow up on the question. No, I fully support, of course, what Peter said. Only just to remark that ultimately, in order to make a decision, you need a threshold. You need a decision criterion. So just to make clear that the interactivity is to be designed in a way that, of course, the threshold criteria is to be set by the user. So, for example, threshold criterion in relation to the sufficiency of certainty on something. So, in that sense, it's the risk under inverted commas of the users to use a specific result, but the innovative element would be to have rather comprehensive information on the quality of the information, and therefore you should be in a position to assess your risk in eventually using it for a decision-making process.
Thank you very much, Christian. I'm going to pass it over to Alison, either for a question or for a follow-up comment.
Yeah, it was a follow-up to the interaction, the bridging that void between the user and the scientific models themselves. We have a really great problem, actually, and that's that Cameron Beccario, who's the creator of EarthNull, and if I've put the link in the chat. If nobody's seen EarthNull, take a look at it. It's just an incredible visualization. And the problem he has is that, he has a day job, so he doesn't have a whole lot of time to develop this. But my vision would be, and it doesn't necessarily have to be this, but it's a great place to start, having that capability of a visual globe. You can move it around, you can click on your area, and having all of the drop down. If you click the Earth word bottom left, you then get the capability to look for aurora, to look for wave height, to look for air circulation. So there's a ton of information that we could actually, the developers could put onto that existing site, and even have that sort of back end where you've got the energy users paying to use this, paying to have the compute behind it, to click on a specific area and have the actual results in however many minutes that the compute that we provide can get the results to them. And so that's just an example. And that kind of interactivity, I think, just for the public is really vital, because that's somewhere where they can go to see, this is where we are expecting in 3 days a torrential downpour that, let's say they're Ugandan, like the FDL use case I put in the chat. You need to go and harvest, otherwise you're going to lose that crop. That's the capability, and having that visualization is really key. And my colleague Peter Messmer is going to talk about.
Alison, your mic is flipped off there for a second, just at the end.
Yeah, sorry, just to say that Peter Messmer, my colleague, is going to talk about this kind of visualization. But thanks very much, Peter Bauer. That was really, really interesting and informative. Thanks.
Thanks very much. We'll take 2 more questions, and then we'll switch over to the second presentation. I think Francesco had his hand up first. Stephen Ramage has left, so we'll go with Francesco, and then we'll go with Pierre. Francesco?
Yes, thank you, David. Actually, I don't have my hand up, but thank you very much for providing me with this opportunity. I'm really interested about the governance that you are considering for this initiative, and overall the structure, also the architecture, of the system to be put in place. I understand this is a medium long-term project, so probably it's something that is still being discussed. But I think it would be very important and interesting to hear something on that, and also the potential role of the private service providers, taking into consideration their capacity to provide computation power for models and for systems. And I do have a lot of questions, sorry. And also, I think a quite important point is how to assimilate or incorporate in the systems socioeconomic variables and parameters. For instance, for spatially explicit land use, land cover change scenarios, which are really critical for policy and decision making. Thank you.
Yes.
Thanks. Great set of questions, Francesco.
Yeah, maybe I should talk about the last point, and I leave the governance point to Christian. Is that okay?
Sure.
Fine, yes.
The assimilation, I would say, is of the extension of the Earth system into impact sectors. I would see technically functioning in the same way as we decide data assimilation system, for example. Right now we try to optimize a system based on information that we have from Earth system models and Earth system observations. And in the future, I would think we would do the same thing and use Earth system and impact models and Earth system and impact observations to do the same, but within the same mathematical framework. And then the weight you give to the individual components in that optimization problem depends on the quality of the ingredients, and the number and the availability of these observations and models. But fundamentally, it's just an extension of the optimization problem that we are applying today. And so your cost function, or against which you optimize, would not just be an Earth system parameter cost function, but it could include things like economic cost, that you want to minimize, for example, or health impact that you want to maximize in a benefit kind of sense. That's the idea.
Thanks, Peter. Christian, I'm going to ask you just to hold on the governance question. Let's come back to that after the next presentation, if you don't mind.
Okay, sure.
So I'm going to switch over to Pierre Quiblier, and then we'll move on to the next presentation. Pierre, the floor is yours.
Thank you very much, David, and thank you very much, Peter and Christian, for this presentations. That seems really greatly encouraging in bridging our policy science to policy gap. Three very quick questions. One is on the focus of your system. You mentioned climate change, disaster, and climate-related type of issues, and biodiversity. I'm wondering whether you are planning to broaden a little bit the focus and include chemicals, waste type of issues, which may have also significant impact and could complete this system that you are developing. We have, in this case, developed with our colleagues from WHO an integrated health and environment chemical observatory to better predict, prevent, reduce chemicals risks, and where we are aiming a little bit like you to translate our scientific evidence into economic types of argument in order to justify the investment to be made. Two calculators have been developed in order to help our decision makers to speed their decision in reducing these chemicals risks and mobilizing the needed investment. And we will be pleased to further share with you our experience in this regard. And our experience actually, and this is my second question, which is a little bit more policy oriented and technical, is that beyond all the pertinence of a computing system, all will depend largely on how well do you gather the evidence, how well do you gather the knowledge from the various sectors. And it happens to be very, very difficult because it's cumbersome for ministries of environment, for ministries of industry, for ministries of agriculture, for borders officers to have an added reporting requirements, and that is extremely important if we want to have a system that works. So I'm wondering, how do you best envisage to convince all the partners to jump in, to pitch in this system? And the third one, which is more related to the governance and policy, again, when we look at WHO, they spend a lot of time right now, particularly in light of the COVID, in developing alert systems, intermediate alert system for public health, emergency of international concerns. This has huge political implications, and they have a governance structure that all their best governance structures is jeopardized somehow by the impact, the economic impact of the decision they may take based on the science that they have gathered to justify a public health emergency. And when we look at that, most of the root causes of the disease on which they are going to base their decision is not existing yet. And I think that with your system, we have perhaps here an opportunity to develop an environmental alert system that would help our colleagues from partners from the health system to not wait for the full consequences of an environmental disaster to become into a health emergency. So that are my three issues that I would be very pleased to get.
Okay, the last one first, because it's the easiest. I would say yes, yes, and yes. So the alert system supported by information from a digital Earth twin is already trialed in cases. We have done studies on outbreak of malaria at seasonal time scales. So the likelihood of outbreaks of malaria, for example, for seasonal outbreaks based on weather forecasts and soil wetness, because you need open water surfaces for that as well, prediction. So I think that the link between health issues that are related to weather and climate is very easy and very straightforward from our system. So I think that is something that could work in the first phase, or right after operational production already, very easy to implement. The second question was about impact sectors. I'm going backwards here, about impact sectors. We're not building Destination Earth from scratch. In the Earth system science community and Earth system service community, think of Copernicus, there is already a substantial user engagement, in parts actually also supported by the WMO, the World Meteorological Organization, that has a very strong branch working on, how weather information and climate information can be linked to users. So we have a lot of history in this area, which doesn't mean, and functioning service, which doesn't mean it's an easy exercise. So I fully understand why you're asking that question, and that is why in Destination Earth we make a particular aspect, a particular effort to close that gap between applications or impact areas and the science part, which I showed in my second to last slide, and why we have in Destination Earth a specific activity on partnerships. And part of that partnerships is, of course, the science technology business, so building the engine. But another part is really the link to the services, and we imagine that Destination Earth will also provide a breakthrough in the service ecosystem, so that in 5 or 10 years, what we consider services or service level of quality looks different, entirely different compared to today, because of Destination Earth. The first one was about chemical waste. I would say the priority of Destination Earth in the first phase certainly is on weather and climate extremes, and anything you can derive from that. And already, renewable energy, food, water, health, insurance, and finance is a very wide portfolio, that weather and climate is relevant for and that we need to cover. So whether at some stage chemical waste comes into play one way or another is difficult to say right now. I'd say it's not at the top of our list.
Thank you very, very much. And good.
Okay, thanks, Pierre. Thanks, Peter. Let's pause the questions for now, and let's move over to the third presentation from Peter Messmer from Nvidia. Peter, the floor is yours. Messmer. The floor is yours.
No worries at all. Thanks very much, David. So can you let me share the screen, please?
Yes, absolutely. I shall give you the power in 2 seconds. All right, you should have it now, Peter.
Perfect. Thank you. All right, and you should be able to see my slides now.
I see them I see them very well, thanks.
Perfect. Thanks very much. Well, thanks everybody for giving me the opportunity to talk here a bit about the infrastructure, or one of our infrastructures for digital twins. As Peter mentioned before, right, the focus here is going to be a bit more on the visualization side. But let me just go to the next slide to show like how we fit into this whole the whole story. So let's see. All right. So one of the slides that Peter showed was about the 3 different tiers of how the digital twins are being built up. So starting with the digital engine, the digital twin engine, then the actual digital twins, and then the use cases. This was pretty much the way that it was set up, was driven from the core models and how then that becomes wider and wider used. I'd like to go approach it from the other way around and say, what is the user experience of that? And as Peter mentioned as well, right, one of the big components has to be interactivity. You want to be able to explore the data. You want to play through different scenarios. You want to interactively change certain parameters to figure out what happens if you're going, if one thing happens, and what is the outcome on a certain variable. The other aspect is collaboration. Nobody's doing their work by themselves anymore. Different organizations have to share data, to share results that are based on derived quantities. And in order to get to that point, you have to have the on-demand compute capabilities. Again, in the previous presentation, there was a lot of discussion about the need for on-demand compute. But the last element that needs to be addressed is the focus on the end user. So again, those 4 parts should basically be the drivers for the infrastructure. So instead of saying, let's start with a numerical model that that drives ultimately the products, let's look at it from the user's perspective. How can we? What do we need in order to make it a pleasant experience for the end user, for this diverse community of end users, and how can we then take that input and query the databases or trigger simulations on demand? So a slightly different way of just looking at it, exactly the same thing, is to basically just view it as a big coupled system, right? Here in this diagram on the right-hand side, I'm showing different users that are playing through the different scenarios, and they're somehow magically providing input to this infrastructure, and they trigger certain simulations, for instance, on an HPC system, one of those on-demand compute scenarios that Peter described, or they query sensor data coming from satellites or IoT. They can trigger real-time simulations, maybe data-driven models that provide feedback much faster than, let's say, a conventional PDE-based HPC simulation, or they trigger just mundane services for format conversion or data fusion and whatnot. So all of these components are represented by different systems, different locations, and somehow they all magically need to interact with each other. Now, the fun part is that this is not a unique theme to the digital twins in the Earth science. You have a similar scenario, for instance, in when you're building a high-end Hollywood movie or when you're doing a high-end computer game. You basically have ultimately the users who want to watch the movie or who want to play the game, and they have certain requests, and they need to combine their assets, or they need to get assets that are a combination from different artist provided assets or simulation provided assets. There has to be the high-end compute facilities in the picture that render the final frames or that provide the renderings for the simulation. So this all has to work together, and to some degree you can just look at it as a big collaboration between humans and machines, right? And some of the services actually are humans, like the artists who improve the visuals, or it can be just some service that is actually coming from just a piece of software that runs on a separate system. And so right? This type of collaborations have never been as essential in the past, and they're just popping up all over the place. I've mentioned the media and entertainment space. The whole theme of today is basically on the scientific side, but you're seeing this in the manufacturing space, in architecture, and so on. So it's just something where the industry is waiting for common standards and ways to simplify the setup of these type of collaborations. Now, part of these collaborations are workflows. Peter also mentioned that just triggering or running an operational weather forecast model is actually not just typing in a.out on a command line and then you have it, but it's a very complicated piece to get from an initial condition all the way to the final results. That and that's not only in weather forecast the case. That's basically in all kinds of the industrial sectors the case. And one of the challenges is that you have an explosion of tools and applications. Again, this year is geared more towards the graphics space, but everybody uses different tools. All of these tools have their justifications for being there, and you have users of those tools that don't want to switch between them. And so you have to respect that everybody just comes with their own suite of tools, and somehow they all have to work together. Similarly to UNEP's mission with the fact that every sensor and every agency provides their own data in their own format and at their own rates. And so it's probably going to be impossible to just find this common ground that everybody can take somebody else's data without any sort of conversion. The other part is the globally distributed teams. Again, as I've shown in the diagrams before, we cannot assume that something is just sitting in one single location, but it has to, by default, be spread globally. And the last part is just the scale of the projects. Again, when you think about the Twin Earth project, there we're talking about petabytes per day in the amount of data, and computational resources that are in the hundreds of petaflops. So that are scales that are simply unprecedented. But again, the good thing is it's not just one domain that is confronted with that, but it's across the entire industry. And so there is the potential to leverage those technologies across different domains. Especially today with COVID, the remote collaboration part becomes more and more important. I mean, we are currently remotely collaborating, and again, being able to utilize those kind of underlying technologies that enable us to penetrate through different networks, through firewalls, and yet still have our systems secured. We take it for granted when we do these phone calls, but if you ever try to do something like a robust connection establishment between your laptop and a supercomputer, it's oftentimes still a lot of work, and it's very customized work. And it would be really nice if somebody would just take away this burden and solve the problem once and forever, and we can just focus on the work that we want to do. And so these type of challenges are also something that appear throughout the entire industry. And so as a consequence, Nvidia basically decided to build a solution for ourselves. Again, we're as a sizable company that is spread across many different domains, from computer graphics via artificial intelligence, self-driving cars, chip building, and so on. We're covering the entire technology space, and so people are spread across the globe, and we're facing exactly those types of problems that I've described before. And so we wanted to have a solution to connect our teams and bring this real-time collaborative experience to ourselves. The other part is that we want to have mechanisms to streamline the product development, and we want to be able to connect to all the different tools that the industry has to offer. So again, the fact that we don't believe that there's just one tool that everybody should use. No, we have to embrace diversity and just accept the fact that there needs to be transformations between different assets, but we want to make sure that those transformations are actually done in a secure, in a safe and reproducible way. And then the last part is that we do build a lot of technologies, and we want to make those technologies available to ourselves. And so having a mechanism of just coupling all these different technologies together, gives us an opportunity to grab those results across the company. And so the result of this was what we call Omniverse. Omniverse is basically this technology that, or this platform that allows us to bring different technologies together, have connectors to the outer world. So it allows us to couple to arbitrary applications, arbitrary content providers. We augment them with our technologies, and we provide portals that allow an end user to access those technologies through a unified interface. And so the goal here is really to build this infrastructure that allows anyone to hook up and combine and share assets and offer services on top of that. Now, this platform from the beginning has been designed from, again, for the cloud. Given that it's only been about maybe 3 years now since the first ideas floated around, it was clear that workstations or desktop computers or laptops, that's no longer the unit that we should think about, but those are just portals into the actual world. But the platform itself should be cloud native, and it has to be scalable. It has to be, in our case, multi-GPU enabled, and there has to be a way of using open standards. And so to allow to have workflows that anyone can access and anyone can use. And so here is just a fairly dense diagram about the entire software stack that we have on the Omniverse platform. But and I'll get into some of the components later on. At a later time, I'd be happy to go into more detail. But at the end of the day, what we're talking about is a combination of hardware resources, graphics, compute, and AI resources, all accessible with the same platform. And again, thinking about your specific problem, it's very much very similar to that, in the sense that you want to find a platform that allows you to combine all these different data sources from all the different data providers, act on those with certain algorithms or compute on them, and some of them being artificial intelligence based, some of them are more conventional high performance computing, and ultimately you want to do some visualizations on them. Just the only slide where I talk about our hardware. One of the beauties of a cloud native platform, and especially a containerized platform, is that it can be deployed on pretty much any arbitrary systems. And so that can go from consumer grade hardware all the way up to supercomputers based on our technology. I should also mention that, again, that's this technology, or our technology is really just the optimization part, the way that the platform is optimized. Nothing prevents you to use the Omniverse infrastructure on a CPU-based system or a couple different types of systems from different vendors together. So nothing about the platform itself is really exclusive on our platform. However, when it comes to the graphics and rendering components, those are obviously geared towards the Nvidia platform. Now, people have, over the past 2 years, built a broad range of applications on top of that. So that goes from game developers and even games all the way to architecture, demonstration examples, or robotics training infrastructures. Again, that's one area that's currently very hot, which is training of or synthetic training of robots using high performance compute resources. Now, what's in the box? When you look at the Omniverse platform, again, I've posted a link earlier on. When you download Omniverse, you basically get 4 or 5 components. One is the core services. So that's the engine that couples all the different pieces together, and that keeps track of who wants to make some changes, who wants to signal some changes to its partners, and so on. So that's the you can think of it almost like a distributed database that acts as the core service. On this platform, you have different tools, different clients that can connect to it. One of them is our high-end rendering engine. And I know you're probably not so much into the rendering aspects, at least not as much as the let's say the movie industry. But I hope I can convince you that even high-end rendering in the science domains can play a role. We have an editor framework that also connects to those core services, and then we have an API or an SDK that allows us to build those couplers to hook arbitrary third-party applications to it. And so you can build web services that will talk to Omniverse. You can build, just take whatever application you have and let it talk to the Omniverse infrastructure. And the last component is an SDK for building services. I've just mentioned here the real-time physics service, but in theory, you can use the same infrastructure to trigger an HPC application, so the submission of a job on an HPC system, or it can be an arbitrary on-demand compute service that you would trigger via such a service infrastructure. So those are the individual components that are part of the Omniverse platform. Now, I've mentioned the visualization part, and that you again, it's sometimes a bit question of why should we focus so much on the visualization. As said at the beginning, a part of the digital twin is that it enables end users who are not domain scientists to take advantage of the information that's contained in all these data collected by sensors or simulation output. That also means that the way that this data is presented depends on the audience, and you can have a broad range of tools these days to feed or to create the assets in a way that's consumable by the end user. So if you're talking to a hardcore expert, well, the only thing that you need in terms of visualization is maybe a printf statement somewhere in your code to get the numbers that you're looking for. On the other hand, if you're talking to the general public, you probably want to have some visual frills that convey the information nicely packaged and in a way that's very much accessible to the end user. And in many cases, right, in the past, those tools were really living in completely separate ecosystems. But having a platform like Omniverse allows you to couple those again together and ultimately use the tool that's best suited for a specific audience. Now, one of the things we're often talk about is for instance, ray tracing. Ray tracing is this technology where you basically run a simulation to generate pictures from the raw data. And again, you all know it from the movie industry, but here is just one example where to show that ray tracing is not only for making pretty pictures, but even in the scientific space, it helps you to convey more information about the data that you have. And again, coming back to this original mission that we want to make sure that the data that's being communicated contains as much meta information as necessary, so that the user is not confused by the quality of the results. Tool or technologies like ray tracing and all the added visual cues that you get from ray tracing can help to convey all that information. So just to explain here, on the right-hand side, this is a conventionally rasterized image, and on the left-hand side, we have a ray traced image. And when you stare at the two data sets, right on the right-hand side, you see you hardly can notice this rim on the top right that just pops out at you in the ray traced image, or the perception of depth as we have in the lower left corner is something that's completely lost in the conventional rendering technique. To get a bit closer to the Earth sciences, this is actually simulation output from one of ECMWF's models. On the left-hand side, we have the cloud field rendered with a more conventional volumetric rendering engine, and well, you see some structure, but it's pretty much it's pretty much just white, and in some cases you can see through the cloud field. In the right-hand image, we're using a much more sophisticated rendering engine, again part of the Omniverse renderer, and you see a lot of the fine structure here, and so you get a more intuitive understanding of what's happening in the simulation output. And now I'm not sure. I have a bunch of movies, and it's probably going to be a bit jerky across Zoom, but it's the again, bear with me. On the left-hand side, this is basically a user interacting with such a cloud field. So you have full interactivity in the entire 3D space. Now, one of the challenges, especially for climate simulations, is the vast amount of data, or the sheer size of those data sets. And so one technique that we're using, even for volumetric data, is that we're tiling those large data sets, and we're only showing the components that are in the field of view of the user. And so again, that's a mechanism that's enabled by the fact that we're not just relying on the data that's being provided by the simulation, but we can have active services that are being triggered from the user to then go out and chop up the data in a way that's more manageable, smaller, and can be rendered at a much higher rate. So that's for the interactive visualization here. Now let me go to this one, and again, here is just a bunch of examples of the type of visualizations that we can do in 3D space. Again, the fact that we're using ray tracing allows us to have very sophisticated lighting effects. We can do combination of all different visual modes, different quantities. So on the top left side, we have streamlines and geometries provided by some third-party and cloud fields all meshed together. Or we have more conventional arrows to indicate velocity fields. So there's a whole wealth of scientific visualization modalities that we've been developing within the framework of Omniverse. Or here is an example of interactive global data visualization. Right, what I've shown before was always at the local or regional scale. So this is now a global simulation output. Again, you all have seen movies of simulation output, but the cool thing here is that it's truly interactive. The user can play with it. So we have the global projection in the front and a planar projection in the back. And given that at this point the data sizes are becoming relatively small, we can even scrub forward and backward through time. So you get a very an interactive exploration of the data at hand. And now I know that especially the UNEP people here, you are not typically in the three-dimensional space. Obviously, the world is three-dimensional, and I still would claim that there is benefit of using the third dimension on top of the planar two dimensions to show information. And so as an experiment, we just basically took MapX data and imported it into Omniverse as well. And you can see how that this type of data can be visualized as well. So here is like the human pressure in one of the quantities that we found in MapX, right? And being now rendered on top of a a planar surface. And again, we now have the benefit that we can go full 3D with that. We can lift those quantities on top of each other and show multiple of them concurrently. I'm not a GIS expert. I don't have a GIS expert in my team, but again, we'd be very interested in finding out what kind of capabilities would be useful to you and how we could take this infrastructure to make sure that it's of benefit to you. Again, in terms of accessibility, right, we've looked into high-end rendering technologies. Not everybody has a rendering supercomputer under their desk. The good thing is that all this rendering technology is cloud-enabled, as I said at the beginning, and so all the rendering can happen on a machine somewhere far away, and you're just streaming your data to your client. And that also allows us to do things like working inside Jupyter notebooks. So we can, here's just a diagram on how this can be set up. So you have your web browser running on a thin client, and we can basically trigger renderings from within the Jupyter server, fire up or push those into the Omniverse server. This one gets notifies the rendering server, and the visuals get back into the thin client. Very complicated diagram. Yes.
I'm just going to jump in. It's like I can see we're approaching the deadline for the session. If colleagues need to leave, please go ahead and leave. But we're going to continue on for a bit longer to finish Peter's presentation and then continue with some questions and answers.
Yep, and it shouldn't be much longer here. So, right, and so that was just for the accessibility in terms of Jupyter notebooks. One of the important pieces that we had at the beginning was the what-if scenarios, also in terms of the interactivity. And so I just want to give here an example of the combination of real physics and, in this case, real-time physics, what's also called game physics. So it's the physics that's typically being used in computer games. So here on the right-hand side, for instance, we have this power plant. And we can right, the plume from the power plant is just using game physics to simulate it, but we can now play with this like with the wind vector in the vicinity of the cooling tower, so we can actually see what impact it would have on the lighting conditions in the surroundings. At the moment, this is driven by a human who just messes around with the wind vectors. But that can easily be combined with the simulation output from, let's say, a weather forecast that predicts the wind field for this particular location. So at the moment, we see have the cloud field there on top of it as well. So the idea being, again, the combination of real-time physics with the real physics can allow you to play with different scenarios, either with different physical scenarios or just playing with different lighting conditions. Again, that's something that's particularly important in the architecture and engineering space, but also could be of impact in the communal space if you want to better understand where what the lighting conditions are in the city, and then also what impact certain architectural modifications would have. So that's just as an example for what-if scenarios. And again, the idea here is that we can combine either with real-time physics that's used in the entertainment industry, or it could also be combined with machine learned or an AI model that would be more data-driven, and so fuse the output from those different data sources together. I have a bunch more examples, but I would like to, due to the time, I would like to hop on to the end and basically just say where, oops, yes. So where we are, again, I hope I could say that, show you that there's quite a bit of overlap in the requirements for Destination Earth, but I guess for pretty much any digital twin that we have in the environmental space with, let's say, the workflow challenges that we're also seeing in the industry, and that Omniverse can act as a platform for collaboration, for the interactive collaboration and for simulation, and that it can help as a to bring the user experience to the whole to the table, right? Because we're not trying to add a user experience onto a historically more batch-oriented workflow, but rather flip it around, that we say, let's start with a highly interactive workflow as we experience in, let's say, computer games, and then and add the scientific capabilities on top of that. And yes, I'd be very interested to learn from you all what the requirements would be to make this more useful in your space. And with that, thanks very much.
Well, Peter, thank you very, very much for that detailed presentation. I think the first question that must be burning in people's minds is the cost of using Omniverse. Did I catch it correctly that it's an open source platform? Or is there a fee or a cost structure to it?
It's not an open source platform, but it's an open platform. So at the moment, you can download it for free from our website. It is a very new platform, and so I should say it's not 100% clear where the business model goes for Omniverse. One of the ways of looking at it is that it's being viewed as the web for 3D content, and nobody wants to make the web per se for fee, right? Everybody wants to keep that one as open as possible. It only works if it's as accessible as possible. But that doesn't prevent anyone from building services on top of that might be for fee.
Right. It seems like it's a combination of a 3D visualization platform plus with a massive emphasis on interoperability. So it's sort of solving two problems at once. Is the idea that Omniverse becomes that interoperability platform within Destination Earth, or is that a conversation that still has to happen?
That conversation still needs to happen. We'd obviously be very interested, at least, to be part of that. But yeah, that's a conversation that we should have amongst us.
Okay, great. I can see a number of hands up. I'm going to move around. I can see Abdelmenem has his hand up. Abdelmenem, do you want to take the floor, please?
Yes, David, thank you very much. Thank you, Peter, for the great presentation, and also the other colleagues, the other panelists. I was listening very, very careful to this presentation. This is really helpful and very informative. I'm coming from a region that has, less technology, but has another, environmental, let's say, challenges in West Asia, in the Arab region. One of these, let's say, climate-related challenges is the dust storms. And my question is, how can we in this region benefit from this, high-tech technology and the, artificial intelligence in addressing and monitoring, understanding, the dust storms in our region? Thank you very much.
Thank you. That could go to either Peter, or Alison, whoever feels comfortable taking that one.
Maybe I can start. Particularly for dust and sandstorms, there's actually a long history of observation and simulation capabilities in weather. So most weather prediction systems actually have dust observation, simulation, and prediction capabilities, and they have reached service level. So that exists. It's not something that has to be created from scratch. There's certainly something to say about improvements there in terms of predictive skill and spatial resolution and these things. But I would say if that was the challenge, then I would say that we easily or happily pick that up because we know we can.
But maybe to add to this one on a right that depending on the questions that you're trying to answer, but it could also be one of the places where again, game physics could start to play a role as well, in the sense that if you want to understand how a dust storm or a sandstorm acts around your buildings or in your city, that might be a place where you don't need to have a super high accuracy, but it's sufficient to be, or it's probably even better to be just highly interactive, to play through different scenarios and use the output from a weather model to get at least the coarser scale wind fields, but then at the small scale, especially around complex topography, you could use more interactive models.
Thanks, Peter. I think one of the great things about both your presentations has been this focus on this combined focus on sort of end user and understanding the value chain to the end user, and then also thinking through that interface and that usability. And I think those are two lessons that UNEP really needs to take away from both of these presentations. I think we're at the point that Peter said, where we're providing data, different kinds of environmental data, but not actually thinking through that value chain to how that data is potentially then taken up and actually influencing decision making. I think there's still a gap there. So I really appreciate that focus. I wanted to flip it back to this governance question. I think it's a big one, perhaps too big to to conclude with, but I wanted to ask if Christian wanted to come in on this broader question of governance with a few final thoughts. Sure.
Well, I mean, what we have learned from a number of past projects is that whatever the governance is, and this has not yet been defined in detail, but whatever it is, it needs to be slim and it needs to be open in order to really have an impact and be cost effective. So what that means is, I mean, we are currently developing this model, but essentially the elements will be, I mean, we need to report back to, of course, to where the money comes from, and these are our member states. So there's a role for the member states. There will be a role for, let's say, for a kind of review board of independent experts, which is not supposed to become a club of friends, but an open board, or however we call it, really targeting specific expertise at the time when it is needed. We need to be very open towards the science community, so there needs to be an engagement forum along this line. And with regard to the users, as I think Peter Bauer already mentioned or indicated in his presentations or in the discussion afterwards, we are thinking about a model on how to engage with users via some kind of partnership agreements. And these users could be really along the entire spectrum of stakeholders, including European, including non-European ones, from policy, from science, from business. I'm not sure if I lost you.
David,
No.
you're on mute.
Sorry about that. Yep, I do it once a session. Before we head to Francesco for a final question, there was a question from a colleague about SDG monitoring. And in particular, is Destination Earth going to be geared towards monitoring specific SDGs that could be monitored with this kind of platform? Peter Bauer, did you want to take that question?
You probably could. I mean, if you look how many of those are relevant, for how many of those climate and extremes are relevant, you probably could. And I think the logic is similar to the Green Deal, actually. I mean, the Green Deal is fundamentally an economic and societal transformation program. It's not about Earth system science, but it requires the information that Destination Earth will generate in order to drive some of the decisions that need to be made. And you could think about a similar logic for the SDGs here. Absolutely.
Thanks, Peter. I'm going to hand it over now to Francesco, and then I think we'll start wrapping up. Francesco?
Yes, thank you, David. One of the main challenge I think in general also for UNEP is how to communicate science to decision and policy making, especially when uncertainty is one of the main, underpinning themes behind all these systems and models and algorithms. So my question is about Destination Earth, and whether you will also consider this communication issue or communication module to be included in this Destination Earth.
Thank you, Francesco. Peter, Bauer?
Yeah, I know that Christian has a very strong opinion on this, which I support. So maybe he wants to add to my response. Yeah, this is what I meant earlier with, where we in our field, in weather prediction in particular, we have a very rigorous uncertainty handling framework, and we do that. We deploy this by actually running ensembles of simulations. And these ensembles of simulations are, parallel simulations of the same thing, but it includes perturbations that are equivalent to the unknowns and the uncertainties. So the difference between these individual realizations, then, 50 or 100 different realizations, so 150 or 100 different forecasts, let's say, is a reflection of our uncertainty. And because that is a very nonlinear system, the Earth system is very nonlinear, lots of degrees of freedom, you can actually see that the chaotic nature of the system, produces then uncertainty information that is really, really interesting and as important as the forecast itself in our system. So that was a concept actually developed in weather. So the butterfly example, butterfly in the Amazon rainforest causes a tornado somewhere else, is from weather forecasting. And we have, what we would like to see in the context of the digital twin is that this concept is then, translated through the value chain. So every information generator or translator that follows what we produce would apply a similarly rigorous uncertainty calculation, like an error model, so that at any time in that process, wherever you interface with a system or the data, have a full view of the uncertainty. And this is super important. And by the way, this does not only relate to the random component of the error, but also to systematic errors. Because one problem that we have in climate, for example, that our systematic errors are very large. And we need to know about how large they actually are to then put credit to the signal that we're trying to understand. Yes, and I think Christian has probably a bit more to say about that.
Yes, well, this is indeed something which interests me particularly, this aspect, which also goes a little bit back to my background. I'm originally coming from the nuclear safety assessment world, and I think we have really seen there that with perfect models, which and maybe even perfect data, which is a much easier situation than in Earth's system, obviously. But nevertheless, we have seen that limiting the entire process essentially to an experts for experts discussion leads to virtually nothing and leads to the disappearance of, in this case, an entire sector. Now, so clearly, this science for policy aspect is very much in the focus of Destination Earth. So, to me, the Destination Earth is, very naively saying, is about significantly increasing the precision. It's about combining all that with the impact sectors, which then ultimately leads to a combined statement, so to say, on vulnerability or risk, however you call it. And then the ability to translate the resulting metrics into something which is understandable and which also allows end users, non-expert end users particularly, to assess the risk of using this result for practical decision support, decision-making purposes. which is then ultimately the responsibility of the end user. But in order to have this possibility of assessing the risk, quite a bit of model complexity development activity, so to say, is needed. So this will become for sure an exciting research task.
Thank you very much. We have one final question from Charles. I know Charles has been had his hand up a few times, so I'd really like to give him the final question, and then we'll do the final wrap up. Thanks. Charles?
Thank you, David, and thank you to the two Peters. I think these were been very, very insightful presentations, and I think it is becoming very clear that for a policy person to make a decision, seeing is believing, and this is exactly what we're right now doing. Visualization is to make sure that the policymaker sees and he believes. It is difficult sometimes to convince a policymaker when you're just writing very long memos and briefs. So at least if you can visualize the problem, I think it is easier for a policy maker to understand. So I think in this context, I just would like to emphasize to the two Peters in this design that the principle should be simplicity, especially for the audience in Africa. Once things become very complicated, they easily give up. So the back end, you can make it as complicated as possible, but to the user, simplicity should be what should be coming out of the entire system, so that it is very easy for them to cookie cut part of what they want to demonstrate and apply very simple additional layers and get up secondary products in a very simple manner. And so this leads me to a question which has been at the heart of my listening to this presentation is, at what point are you going to engage the ultimate users of these tools, the national level engagement? Do you have a strategy to start, strategically engaging with national experts so that they can provide input into the final refinement of the tool, which will be more responsive to what the countries are actually expecting to get out of this tool? Do you have a strategy for engagement? Do you want to start, identifying national focal points who can provide feedback into usability of the tool, and the strength and other areas which can be strengthened? This is my question. Thank you.
Thanks very much, Charles. Who would like to take that?
So, from Nvidia's point of view, we have an initiative called AI Nations, which has primarily focused on helping nations all around the world harness the power of artificial intelligence, which is actually my field. But this could equally be the platform that we use to assist any member state to move forward, to put a team of developers together. And I know from personal work that African states, for example, are extremely far ahead in developing, in coding, etc. So this would be simply a case of getting a developer team together to take Omniverse, to take our code, which is all available freely online, and start working to put something together individually. Obviously, we're talking here as well about a central digital ecosystem for the planet, and the UN will take this initiative from the centre and push outwards as well. But any assistance that you'd like as an individual member state, please contact me. I've put my details in the chat, and hopefully that will be passed around to everyone anyway. And we can go from there. As my colleague Peter Messmer said earlier, this is a new platform for us, but we're very used to bleeding edge technology and taking something and developing it extremely quickly and making extremely innovative products, let's say, from this. As Peter said, we haven't yet even decided on what the business model is, but I don't want to hang around. There is a huge sense of urgency here for climate and environmental modelling. There's a lot of work being done in the background that can all be pulled together with this visualization tool So let me know what help you need and we'll take it from there. I also put in chat if it's an academic institution, so you have PhDs or even master's students who could work on some of the development, then we can support them with funding, with GPUs, etc. Please just get in touch, and thanks everybody for your time.
Thanks very much, Alison. I'll leave the final remarks or the final closure to Christian. Christian, if you can just answer the question of stakeholder engagement, what's the timeline? And then if you could just wrap up by thanking our speakers, that would be fantastic.
Right. No, I mean, with regard to the user engagement and user perspective, I mean, Destination Earth is a European project. It's on the basis of it's initiated on the basis of the Green Deal. As I tried to explain, so the prime users are EU policy services in different thematic areas, as well as interested national authorities in the member states. But nevertheless, since I was talking a lot about sustainability and interconnectedness and everything, obviously Europe is not an island, and the Earth system is a little bit larger than the European one. So there is clearly a global dimension to it, which we would be happy to take up in some form, and we would be happy to start discussion on that with UNEP. So this hopefully is the starting point of some form of cooperation along these lines. Well, and having said that, of course, I think a lot the presenters for these great contributions, and last not least the audience for interesting questions and the fruitful discussion. And I really invite everybody to keep in contact and check our website. Just Google Destination Earth and you find it about upcoming events or calls or whatever. Let's keep in touch. Thank you.
Perfect. Thank you, Christian. Thank you, Peter. Thank you, Alison, and thank you everybody for attending, for engaging, and as was mentioned, asking some very thought-provoking questions. Christian, your final conclusion or your thoughts, music to my ears. We'd absolutely love to continue this dialogue and figure out, could there be some kind of collaboration between Destination Earth and the World Environment Situation Room? So let's take that idea forward in the coming weeks and months. And thank you again for co-convening this and really supporting this digital discovery session. So thank you very much.
Thanks, everyone.
Thank you.
Great day.
Bye.
Cheers.
Thank you. Bye. Thank you. Thank you.
Thank you and goodbye.
Thank you. Bye-bye.